In this lecture of the scheduling series, we're going to see dominant resource fair scheduling, which is a new concept that has been invented in just the last few years, but has had a lot of impact. So here we're discussing the problem of scheduling large numbers of jobs across a cluster. For instance, scheduling VMs in a cloud or in a cluster. Different jobs may have different requirements, and these requirements may span multiple resources. So for instance, a job 1 may have tasks where each task requires 2 CPUs and 8 gigabytes. Job 2 may have tasks where each task requires 6 CPUs and 2 gigabytes. So then the questions arise when you have these jobs that are together in a cluster. How do you schedule these jobs in a manner that is fair across different jobs? In other words, how many tasks of each job in this particular example, our example, do we allow in the cluster to run concurrently so that you ensure fairness as far as resource allocation is concerned across different jobs? In fact, what does fairness even mean in this particular case? So dominant resource fairness, or DRF, addresses these questions. It was proposed by researchers from University of California, Berkeley. It proposes the notion of fairness across jobs where the jobs have multi-resource requirements. And the researchers showed that the dominant resource fairness is fair for multi-tenant systems. It is strategy proof. This means that tenants cannot benefit by lying. So if a tenant lies about its requirements, it does not really benefit by it. It can only suffer or just stay where it is. It's also envy-free, which means that a tenant cannot envy the allocation that is given to another tenant in the system. Okay, all of these are desirable properties because they eliminate the tenants from strategizing the system and from gaming the system. So DRF is useful in scheduling virtual machines in a cluster. It's also useful in scheduling Hadoop in a cluster. It's useful wherever you have jobs, and these jobs have tasks which need to be scheduled in a cluster, and the tasks themselves have multi-resource requirements. DRF is used in Mesos, an operating system that was invented by researchers at Berkeley and the operating system is intended as a distributed operating system for cloud environments. And DRF-like strategies are also used in cloud computing operating systems that have been built by several cloud computing companies. How does DRF work? Well, let's look at DRF through our example. So job 1, once again, our example has tasks where each task requires 2 CPUs and 8 gigabytes. We denote that as job 1's resource vector, which consists of 2 CPUs, 8 gigabytes, where 8 gigabytes is the RAM or the memory required by the job. Job 2's task requires 6 CPUs and 2 gigabytes, so its resource vector is 6, 2. Now consider a cloud or a data center which has 18 CPUs and 36 gigabytes of RAM. That's the resource vector of the cloud itself. Now let's look at job 1. So each task of job 1 consumes a percentage of total CPUs, which is, it requires 2 CPUs, and the total number of CPUs in the cloud is 18. So the percentage of the total CPUs consumed by one task from job 1 is 2 by 18, which is 1 over 9. Similarly, each task of job 1 requires 8 gigabytes of RAM. The total RAM present in the cluster is 36, so the percentage consumed by each task of job 1 is 8 by 36, which is 2 by 9. So 1 by 9 is less than 2 by 9, which means that job 1's dominant resource is the orange resource, which is RAM. So job 1 is more memory intensive or RAM intensive than it is CPU intensive. So that's job 1. Let's do a similar calculation for job 2. Job 2's single task consumes percentage of total CPUs, which is 6 CPUs divided by 18 total CPUs, that's 6 by 18. As far as RAM is concerned, each consumes 2 gigabytes of RAM. The total gigabytes of RAM is 36, so that's 2 by 36, which is 1 by 18. Here, the blue value, 6 by 18, is larger than the orange value. And so 6 by 18 is greater than 1 by 18, which means that job 2's dominant resource is CPU. So it is more CPU intensive than it is memory intensive. So job 1's dominant resource was RAM, and job 2's dominant resource is CPU. So different jobs may have different resource types that they are dominant on. And DRF ensures the following property. For a given job, the percentage of its dominant resource type that it gets cluster-wide is the same for all jobs. In other words, you allocate tasks to job 1 and you allocate tasks to job 2 so that the total percentage of RAM that job 1's total tasks get is equal to the total percentage of CPU that job 2's tasks get, because RAM is the dominant resource of job 1 and CPU is the dominant resource of job 2. These constraints can be written as linear equations and solved. We won't go through those equations and solutions here. Let me just tell you the solution for our particular example. Okay, so for our example, the solution turns out to be that job 1 gets 3 tasks, each with the resource vector 2 CPUs and 8 gigabytes, and job 2 gets 2 tasks, each with the resource vector 6 CPUs and 2 gigabytes. Let's ensure that this actually satisfies the DRF fairness rule. So job 1's percentage of RAM is the total number of tasks given to job 1 times the amount of RAM per task, that's the total RAM to job 1, the numerator, divided by the total cluster RAM. So the number of tasks it gets is 3 times 8 gigabytes per task divided by 36 gigabytes, that's 2 by 3. Let's do the similar calculation for job 2's the dominant resource, which is CPU. The number of tasks given to job 2 is 2, the CPU per task is 6 CPUs, divided by the total number of cluster CPUs, which is 18. So that's 2 times 6 by 18, which is also 2 over 3. Okay, so that's the that ensures that job 1's percentage of RAM equals the job 2's percentage of CPU. So every job gets the same percentage of the cluster as far as its dominant resource is concerned. And you can verify that allocating job 1 3 tasks and allocating job 2 2 tasks also satisfies the total number of resources that you have. Right? So job 1 gets 3 times 2 6 CPUs, job 2 gets 2 times 6 12 CPUs, so that's a total of 18 CPUs. You do have 18 CPUs in the system. The RAM given to job 1 is 3 times 8 24. Job 2 gets 2 times 2 4, so that's 28 gigabytes, which is less than the 36 gigabytes you have. So you're using less than the total amount of memory in your system, but that's fine because it's the price you pay for fairness in your system. So DRF, even though we've discussed it only for 2 types of resources, where a resource vector has only 2 components, the CPU and the RAM, it also generalizes to cases where jobs might have multiple resource requirements. It also generalizes to cases where you have multiple jobs, not just 2 jobs in your system. So you can have multiple jobs, and each job can have CPU requirements, memory requirements, also network and maybe even disk requirements, and so on and so forth, and DRF would generalize even to those. DRF essentially ensures that each job gets a fair share of that type of resource which that particular job desires the most, meaning its dominant resource, and this is why DRF is in fact fair across different jobs with multi-resource requirements. So to wrap up our entire discussion of scheduling, scheduling is a very important problem in cloud computing because you have limited resources, typically processor and memory resources, and you have a lot of jobs with tasks that require access to these resources. So which jobs run when on which resources is the scheduling problem. We've discussed classical single process scheduling algorithms such as first in, first out, shortest task first, priority, and round robin. We've also discussed Hadoop scheduling strategies that are popular today, such as Capacity Scheduler and the Hadoop Fair Scheduler. And finally, we've discussed strategies that are fair across multiple tenants in a multi-tenant cloud environment. Especially, we have discussed the dominant resource fairness strategy, which is actually gaining popularity today.